Good evening and welcome. Tonight we are diving into something vast, something ancient, something that has captivated humanity since the first person looked up at the night sky and wondered what those tiny lights really were. We are going to explore the language of space. Every strange word, every confusing term, every bit of cosmic jargon that makes astronomy seem intimidating. We are going to break it all down into simple, plain English. Space is not as complicated as it seems. Yes, the universe is enormous. Yes, the numbers are mind-boggling. Yes, scientists use words that sound like they belong in a fantasy novel. But at its heart, space is just the story of matter and energy doing interesting things over very long periods of time. And that story is one we can all understand. So settle in, get comfortable, and let us journey through the cosmos together. By the time we are finished, you will be able to hold your own in any conversation about the universe. You will understand what astronomers mean when they talk about redshift and event horizons and accretion disks. You will know why some stars explode and others just fade away. And most importantly, you will see just how connected we are to everything out there in the darkness between the stars. Let us begin at the beginning. Let us start with the most basic building blocks of the universe and work our way up to the grandest structures imagination can conceive. Part 1. The basics of space and time. Astronomy. Astronomy is the scientific study of everything beyond Earth. Stars, planets, moons, galaxies, black holes, cosmic dust, dark matter, and everything else floating round in the void. The word comes from the Greek words astron, meaning star, and nomos, meaning law. So astronomy literally means the laws of the stars. Humans have practiced astronomy for thousands of years. The ancient Babylonians tracked the movements of planets around 4,000 years ago. The Egyptians aligned the Great Pyramids with specific stars. The Mayans created calendars so accurate they could predict eclipses centuries in advance. Today, astronomers use telescopes that can see light from galaxies that existed over 13 billion years ago, back when the universe was still young and chaotic. Astronomy is different from astrology. Astronomy is science. Astrology is the belief that the positions of stars and planets affect human behavior and destiny. One is based on evidence and measurement. The other is based on ancient traditions and personal interpretation. They share a common ancestor, but they parted ways long ago. The universe is everything that exists. All matter, all energy, all space, all time. Every galaxy, every atom, every ray of light. If it exists, it is part of the universe. The word comes from the Latin universum, meaning turned into one, or the whole thing. Current estimates suggest the observable universe contains around 2 trillion galaxies, that is, followed by 12 zeros. Each of those galaxies contains anywhere from a few million to several trillion stars. Our own galaxy, the Milky Way, holds somewhere between 100 billion and 400 billion stars. And around many of those stars orbit planets, moons, asteroids, and comets. The observable universe is about 93 billion light-years in diameter. But that is just the part we can see. Light from more distant regions has not had time to reach us yet, since the universe began around 13.8 billion years ago. What lies beyond our observable horizon remains one of the greatest mysteries in science. A light year is a measure of distance, not time. It is the distance that light travels in 1 year. Light moves at about 186,000 miles per second, which is roughly 300,000 kilometers per second. Over the course of a year, light covers about 5.88 trillion miles, or 9.46 trillion kilometers. We use light years because space is so enormous that miles and kilometers become meaningless. The nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. That means the light we see from Proxima Centauri tonight actually left that star over 4 years ago. We are always looking into the past when we look at the stars. When astronomers say a galaxy is 1 million light-years away, they mean that the light from that galaxy took 1 million years to reach us. We are seeing that galaxy as it was 1 million years in the past. The farther we look into space, the deeper we look into history. An astronomical unit is the average distance from Earth to the Sun. That distance is about 93 million miles, or 150 million kilometers. Scientists abbreviate it as O. Astronomical units are useful for measuring distances within our solar system. Mars orbits the Sun at about 1.50. Jupiter sits at roughly 5.2 AU Neptune. The most distant major planet orbits at about 30 AU from the Sun, the dwarf planet. Pluto ranges from about 29 to 49 AU, depending on where it is in its elliptical orbit. Light takes about 8 minutes and 20 seconds to travel 1 astronomical unit. So when you look at the Sun, you are seeing it as it was 8 minutes ago. If the Sun suddenly went dark right now, we would not know for another 8 minutes. A parsec is another unit of cosmic distance. The word combines parallax an arc-second. 1 parsec equals about 3.26 light-years, or roughly 19 trillion miles. The parsec comes from how astronomers measure stellar distances using parallax. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. The amount of shift depends on how far away the star is. A star that shifts by 1 arc-second is exactly 1 parsec away. Professional astronomers often prefer parsecs over light-years because the math works out more cleanly in their calculations. When you hear that a galaxy is 10 megaparsecs away, that means 10 million parsecs, or about 32.6 million light-years. Gravity is the force that pulls objects with mass toward each other. It is what keeps your feet on the ground, what keeps the moon orbiting Earth, what keeps Earth orbiting the Sun, and what holds galaxies together across millions of light-years. Isaac Newton first described gravity mathematically in 1687. He showed that every object with mass attracts every other object with mass. The strength of this attraction depends on 2 things: how massive the objects are and how far apart they are. Double the mass, double the gravitational pull, double the distance, and the pull drops to 1/4. Albert Einstein revolutionized our understanding of gravity in 1915 with his theory of general relativity. Einstein showed that gravity is not really a force at all. Instead, massive objects bend the fabric of space and time around them. Other objects follow curved paths through this bent space-time, which we perceive as gravitational attraction. A bowling ball on a trampoline creates a dip, and marbles roll toward it. Massive objects do the same thing to space itself. An orbit is the curved path one object takes around another under the influence of gravity. The moon orbits Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way galaxy. Even galaxies orbit each other in vast cosmic dances that take billions of years to complete. Objects in orbit are actually falling continuously. The moon is falling toward Earth every moment, but it is also moving sideways fast enough that it keeps missing. The curve of its path matches the curve of Earth beneath it. This is the secret of orbit, falling forever but never hitting the ground. Earth completes one orbit around the Sun every 365¼ days. That is why we have leap years every 4 years to account for that extra quarter day. The moon takes about 27.3 days to orbit Earth. the International Space Station, orbiting just 250 miles above the surface, circles Earth every 90 minutes. Vacuum. A vacuum is space that contains little or no matter. The space between stars and galaxies is not truly empty, but it is incredibly close. In the best laboratory vacuums on Earth, there might be a few thousand molecules per cubic centimeter. In interstellar space, that drops to about 1 atom per cubic centimeter. In the voids between galaxy clusters, it drops even further. The vacuum of space presents unique challenges. Without air pressure, liquids boil at extremely low temperatures. Human blood would not actually boil, because our skin provides enough pressure, but exposed water would turn to vapor almost instantly. Without air to carry sound, space is completely silent. Explosions happen in total silence. There is no up or down, no hot or cold winds, no weather of any kind. Despite being nearly empty, the vacuum of space is not nothing. Modern physics tells us that even empty space seethes with quantum fluctuations, virtual particles popping in and out of existence too quickly to measure directly. The vacuum has energy, and this vacuum energy may be driving the accelerating expansion of the universe. Part 2. Stars and Stellar Phenomena. Star. A star is a massive ball of hot gas held together by gravity and powered by nuclear fusion in its core. Stars are the most important objects in the universe for life as we know it. They create the heavy elements that make up planets and people. They provide the light and heat that allow life to exist. Every atom in your body heavier than hydrogen was forged inside a star. Pressed stars form when clouds of gas and dust collapse under their own gravity. As the material falls inward, it heats up. Eventually, the core becomes hot enough and dense enough for hydrogen atoms to fuse into helium, releasing enormous amounts of energy. This energy pushes outward against gravity, and the star reaches a stable balance that can last for millions or billions of years. Our Sun is a fairly average star, a yellow dwarf about 4.6 billion years old. It will continue fusing hydrogen for another 5 billion years before expanding into a red giant and eventually fading into a white dwarf. More massive stars burn brighter but die younger, sometimes in spectacular explosions called supernova. Nuclear fusion. Nuclear fusion is the process of combining light atomic nuclei into heavier ones, releasing tremendous energy in the process. This is what powers every star in the universe, including our Sun. In the core of the Sun, temperatures reach about 15 million degrees Celsius. At these extreme conditions, hydrogen nuclei move so fast that they overcome their natural electrical repulsion and slam into each other hard enough to fuse. For hydrogen nuclei combine to form one helium nucleus, and the tiny bit of mass that disappears in the process converts into energy according to Einstein's famous equation relating energy to mass times the speed of light squared. Every second, the Sun converts about 600 million tons of hydrogen into helium. About 4 million tons of mass disappear entirely, transformed into pure energy. This energy works its way from the core to the surface over hundreds of thousands of years, eventually radiating into space as the sunlight that warms our planet. Nebula. A nebula is a giant cloud of gas and dust in space. The word comes from the Latin word for cloud or mist. Nebulae are some of the most beautiful objects in the universe, glowing with vivid colors that span hundreds of light years. There are several types of nebulae. Emission nebulae glow because hot young stars inside them ionize the surrounding gas, causing it to emit light. B. Orion Nebula, visible to the naked eye as a fuzzy patch in the constellation Orion, is a famous emission nebula about 1,340 light-years away. It is a stellar nursery where new stars are being born right now. Planetary nebulae form when dying stars shed their outer layers. Despite the name, they have nothing to do with planets. Early astronomers thought they looked like planets through small telescopes. The Ring Nebula and the Cat's Eye Nebula are beautiful examples. Supernova remnants are nebulae created by exploding stars, like the famous Crab Nebula, which formed when a star exploded in the year 1054. Protostar. A protostar is a young star that is still forming, not yet hot enough in its core to sustain nuclear fusion. It represents the earliest stage in a star's life, when gravity is pulling gas and dust together, but the fusion furnace has not yet ignited. Protostars form inside dense cores within molecular clouds. As material falls inward, it releases gravitational energy as heat. The protostar glows in infrared light, to cool and shrouded in dust, to be visible in normal light. This phase can last anywhere from a few 100,000 years to 1,000,000 years, depending on how massive the forming star is. Once the core reaches about 10 million degrees, hydrogen fusion begins, and the protostar officially becomes a star. The sudden release of energy clears away the surrounding gas and dust, revealing the newborn star to the universe. Not all protostars succeed. Some never gather enough mass to ignite fusion and become brown dwarfs instead. Main sequence. The main sequence is the longest and most stable phase in a star's life, when it fuses hydrogen into helium in its core at a steady rate. Most stars you see in the night sky are main sequence stars, including our Sun. How long a star stays on the main sequence depends entirely on its mass. Small red dwarf stars burn their fuel slowly and can remain on the main sequence for trillions of years, far longer than the current age of the universe. Our Sun will stay on the main sequence for about 10 billion years total, and it is roughly halfway through. Massive blue stars burn so hot and fast that they exhaust their hydrogen in just a few million years. When astronomers plot stars on a graph comparing their brightness to their temperature, main sequence stars form a diagonal band from hot, bright blue stars in the upper left to cool, dim red stars in the lower right. This pattern, called the Hertzsprung-Russell diagram, is one of the most important tools in stellar astronomy. Red giant. A red giant is an aging star that has exhausted the hydrogen fuel in its core and begun fusing hydrogen in a shell around the core. This causes the outer layers of the star to expand enormously while the surface cools, giving the star its characteristic red color. When our Sun becomes a red giant in about 5 billion years, it will swell to perhaps 200 times its current size. Its outer edge will extend past the orbit of Mercury and Venus, possibly even reaching Earth's orbit. The inner planets will be vaporized, even if Earth survives. The intense heat will boil away the oceans and strip away the atmosphere. Red giants eventually shed their outer layers into space, forming beautiful planetary nebulae. What remains is the hot, dense core, which cools over billions of years into a white dwarf. More massive stars skip the red giant phase and become supergiants before exploding as supernova. White dwarf. A white dwarf is the dense, Earth-sized remnant left behind when a medium-sized star like our Sun dies. Despite being roughly the size of Earth, a white dwarf contains about the mass of the Sun, making it incredibly dense. A teaspoon of white dwarf material would weigh several tons. White dwarfs no longer generate energy through fusion. They shine only because they are still hot from their former lives as normal stars. Over billions of years, they slowly radiate away their heat into space, eventually becoming cold, dark objects called black dwarfs. However, the universe is not old enough for any black dwarfs to exist yet. The first white dwarfs ever formed are still cooling. The matter inside a white dwarf exists in a strange state called electron-degenerate matter. The electrons are packed so tightly that quantum mechanical effects prevent further collapse. There is a limit to how massive a white dwarf can be, about 1.4 times the mass of the Sun. Any more massive, and the electron pressure cannot hold against gravity. A supernova is the catastrophic explosion of a star, one of the most violent events in the universe. For a brief time, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. There are two main types. Core collapse supernova happen when massive stars, at least 8 times the mass of the Sun, run out of fuel. Without the outward pressure from fusion, the core collapses in milliseconds. The outer layers crash inward, hit the suddenly rigid core, and rebound outward in a tremendous explosion. Type Ia supernova happen when a white dwarf in a binary system accumulates too much mass from its companion star. When it exceeds the limit of about 1.4 solar masses, it explodes completely. Supernova are cosmic forges. The extreme temperatures and pressures during the explosion create heavy elements like gold, platinum, and uranium that cannot form inside normal stars. Every atom of these elements on Earth came from supernova that exploded billions of years ago. We are quite literally made of star stuff. Neutron Star. A neutron star is the collapsed core left behind after a massive star explodes as a supernova. It is made almost entirely of neutrons, particles found in atomic nuclei, packed so tightly that a neutron star only about 12 miles across contains more mass than the Sun. The density of neutron star material is almost beyond imagination. A sugar cube-sized chunk would weigh about 1 billion tons on Earth. The gravity at the surface is about 200 billion times stronger than Earth's gravity. If you dropped an object from 1 meter above a neutron star's surface, it would hit at about 2 million meters per second. Many neutron stars spin incredibly fast, some rotating hundreds of times per second. They also have extremely powerful magnetic fields, trillions of times stronger than Earth's. When these spinning magnetic fields sweep beams of radiation across space like cosmic lighthouses, we call them pulsars. A pulsar is a rapidly rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. As the star spins, these beams sweep through space like lighthouse beams. If one of the beams happens to sweep across Earth, we detect regular pulses of radio waves, X-rays, or gamma rays. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. The signals were so regular that the astronomers briefly wondered if they had detected alien communications. They nicknamed the first pulsar LGM-1, standing for Little Green Men. We now know of over 3,000 pulsars in our galaxy alone. The fastest known pulsars, called millisecond pulsars, spin hundreds of times per second. Their rotation is so stable that they rival atomic clocks for precision. Astronomers use networks of pulsars as a kind of cosmic GPS system, and even to detect gravitational waves passing through our region of space. Part 3. Black holes and extreme objects. Black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole from which escape becomes impossible is called the event horizon. Once something crosses the event horizon, it is gone forever from our universe's perspective. Black holes form when massive stars die. If the collapsing core is massive enough, around 3 times the mass of the Sun or more, even neutron degeneracy pressure cannot stop the collapse. The matter crushes down to a single point of infinite density called a singularity, surrounded by the event horizon. Black holes come in different sizes. Stellar black holes formed from dying stars typically have masses between 5 and 50 times the Sun. Supermassive black holes, found at the centers of galaxies, can contain millions or billions of solar masses. The supermassive black hole at the center of our Milky Way, called Sagittarius A star, has a mass of about 4 million suns. Event horizon. The event horizon is the boundary around a black hole beyond which nothing can return. It is not a physical surface you could touch. It is simply the point of no return, where the escape velocity equals the speed of light. From the outside, the event horizon appears as a perfect black sphere. Any light that approaches it either falls in or bends around the black hole without reaching us. This creates a dark silhouette against the background of space and any glowing matter nearby. Time behaves strangely near the event horizon. From a distant observer's perspective, an object falling toward a black hole appears to slow down as it approaches the horizon, never quite reaching it. The falling object would see something different. It would cross the horizon in finite time and fall toward the singularity. This is one of the strangest predictions of Einstein's general relativity. A singularity is a point where the laws of physics as we know them break down. At the center of every black hole, according to general relativity, all the mass is crushed into a point of zero volume and infinite density. This is the singularity. The singularity is one of the greatest mysteries in physics. General relativity predicts it must exist, but the mathematics produces nonsensical, infinite values. Most physicists believe that a complete theory of quantum gravity, which we do not yet have, will reveal what actually happens at the singularity. Perhaps there is no point of infinite density. Perhaps the matter transforms into something else entirely. We simply do not know. The Big Bang singularity is another famous example. All the matter and energy in the observable universe appears to have originated from an infinitely dense state about 13.8 billion years ago. Understanding singularities may be the key to understanding the origin of everything. Accretion disk. An accretion disk is a flat, rotating disk of gas, dust, and other matter spiraling into a massive object like a black hole or young star. As material falls inward, it does not drop straight down. Angular momentum causes it to form a disk, like water spiraling down a drain. Accretion disks around black holes can be incredibly hot and bright. Friction between the swirling layers of gas heats the material to millions of degrees. The inner parts of the disk glow in X-rays, while outer regions emit ultraviolet and visible light. A supermassive black hole's accretion disk can outshine the entire galaxy around it. The famous first image of a black hole, released in 2019, actually showed the glowing accretion disk around the supermassive black hole in the galaxy M87. The black shadow in the center is the event horizon, surrounded by the brilliant ring of superheated matter. Hawking radiation. Hawking radiation is a theoretical prediction that black holes are not completely black. They slowly emit particles and radiation, gradually losing mass over immense timescales. This idea was proposed by physicist Stephen Hawking in 1974. The mechanism involves quantum mechanics. Near the event horizon, pairs of virtual particles constantly pop in and out of existence. Usually, they annihilate each other instantly. But occasionally, one particle falls into the black hole while the other escapes. The escaping particle carries away a tiny bit of energy, which appears to come from the black hole's mass. For a stellar black hole, Hawking radiation is incredibly weak, far too faint to detect. A black hole the mass of the Sun would take about 10 to the power of 67 years to evaporate completely. But the prediction has profound implications. It suggests that information falling into a black hole might eventually leak back out, raising deep questions about the nature of information and the fundamental laws of physics. Quasar. A quasar is an extremely luminous, active galactic nucleus powered by a supermassive black hole consuming vast amounts of matter. The name is short for quasi-stellar radio source because early astronomers thought they looked like stars. Quasars are among the brightest and most distant objects in the observable universe. The energy output of a quasar is staggering. A single quasar can outshine 1 trillion ordinary stars combined. This light comes from the tremendous heat generated in the accretion disk around the central black hole. Matter spiraling inward at nearly the speed of light releases vast amounts of gravitational energy. Most quasars existed in the early universe, when galaxies were young and supermassive black holes had abundant fuel to consume. Looking at distant quasars is like looking back in time to an era when the universe was more violent and chaotic. The most distant known quasar is over 13 billion light-years away, showing us conditions less than 1 billion years after the Big Bang. Part 4. Our Solar System. Solar System. Our solar system is the collection of objects bound by the sun's gravity. It includes 8 major planets, at least 5 dwarf planets, hundreds of moons, millions of asteroids, billions of comets, and countless smaller objects. The Sun contains about 99.8% of the total mass. The solar system formed about 4.6 billion years ago from a giant cloud of gas and dust called the solar nebula. Something, perhaps a nearby supernova, triggered the cloud to collapse. Most of the material fell to the center to form the Sun. The leftover material flattened into a disk and gradually clumped together to form the planets. The inner solar system contains the rocky planets Mercury, Venus, Earth, and Mars. Beyond Mars lies the asteroid belt. The outer solar system contains the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. Beyond Neptune lies the Kuiper belt, home to Pluto and other icy bodies, and the distant Oort cloud. Planet. A planet is a celestial body that orbits a star, has enough mass for gravity to make it roughly spherical, and has cleared its orbital neighborhood of other debris. This definition, adopted by the International Astronomical Union in 2006, is why Pluto was reclassified as a dwarf planet. Our solar system has 8 planets. The 4 inner planets are small, rocky, and dense. Earth is the largest of these, with a diameter of about 7,900 miles. The 4 outer planets are much larger, made mostly of gas and ice. Jupiter, the largest, has a diameter of about 86,900 miles, more than 11 times Earth's diameter. Thousands of planets have been discovered orbiting other stars. These exoplanets come in an astonishing variety of sizes, compositions, and orbital configurations. Some are rocky like Earth. Some are gas giants like Jupiter. Some orbit so close to their stars that their surfaces are molten rock. Others drift alone through interstellar space, ejected from their home systems long ago. Dwarf planet. A dwarf planet is an object that orbits the Sun and has enough mass to be roughly spherical, but has not cleared its orbital neighborhood of other debris. This is what distinguishes a dwarf planet from a full planet. Pluto is the most famous dwarf planet, once considered the 9th planet. It was reclassified in 2006 after astronomers discovered that the outer solar system contains many similar objects. Pluto shares its orbital neighborhood with thousands of other icy bodies in the Kuiper Belt. Other recognized dwarf planets include Eris, which is slightly smaller than Pluto but more massive. Makemake and Haumea are also in the Kuiper Belt. Ceres, located in the asteroid belt between Mars and Jupiter, is the only dwarf planet in the inner solar system. Some astronomers believe there may be hundreds of dwarf planets waiting to be discovered in the outer solar system. Moon. A moon is a natural satellite that orbits a planet or other body. Our solar system contains at least 290 known moons, with more being discovered regularly. Jupiter alone has at least 95 known moons. Saturn has at least 146. Earth's moon is the 5th largest moon in the solar system, with a diameter of about 2,159 miles. It is the only celestial body beyond Earth that humans have visited. The moon formed about 4.5 billion years ago when a Mars-sized object collided with the young Earth, blasting debris into orbit that eventually coalesced. Some moons are among the most interesting places in the solar system. Europa, one of Jupiter's large moons, has a global ocean of liquid water beneath its icy surface. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane on its surface. Enceladus shoots geysers of water ice into space. Any of these could potentially harbor life. Asteroid. An asteroid is a rocky object orbiting the Sun, smaller than a planet. Most asteroids in our solar system are found in the asteroid belt between Mars and Jupiter, though many others exist elsewhere. The total mass of all asteroids combined is less than 5% of the Moon's mass. Asteroids are leftovers from the formation of the solar system, chunks of rock that never assembled into a planet because Jupiter's gravity kept stirring them up. The largest asteroid, Ceres, was reclassified as a dwarf planet in 2006. It has a diameter of about 590 miles. Most asteroids are much smaller, just a few miles or even a few feet across. Some asteroids pass close to Earth and are called near-Earth objects. Scientists track these carefully because a large asteroid impact could cause catastrophic damage. An asteroid about 6 miles across struck Earth 66 million years ago, contributing to the extinction of the dinosaurs. Programs like NASA's Planetary Defense Coordination Office monitor potential threats and develop deflection strategies. A comet is a small, icy body that develops a glowing coma and tail when it approaches the sun. Comets are sometimes called dirty snowballs because they are made mostly of ice mixed with dust and rock. Most originate in the outer solar system, in the Kuiper belt or the distant Oort cloud. When a comet approaches the sun, solar radiation heats the ice and causes it to sublimate, turning directly from solid to gas. This creates the coma, a fuzzy cloud of gas and dust surrounding the comet's solid nucleus. The solar wind pushes this material away, forming 1 or 2 tails that can stretch millions of miles through space. Halley's Comet is the most famous periodic comet, returning to the inner solar system every 75 to 79 years. It was last visible from Earth in 1986 and will return around 2061. Comets may have delivered much of the water in Earth's oceans and possibly even the organic molecules that led to life. Meteor, meteoroid, and meteorite. These 3 terms describe the same object at different stages. A meteoroid is a small rocky or metallic body in space, typically smaller than an asteroid. A meteor is the streak of light produced when a meteoroid enters Earth's atmosphere and burns up. A meteorite is any piece that survives the journey and lands on Earth's surface. Most meteors are tiny, ranging from the size of a grain of sand to a pebble. These burn up completely about 50 miles above the surface, producing the shooting stars we see on clear nights. Larger objects can create brilliant fireballs and even explode in the atmosphere with tremendous force. In 2013, a meteoroid about 66 feet across exploded over Chelyabinsk, Russia. The airburst released energy equivalent to about 500 kilotons of TNT, shattering windows and injuring over 1,500 people. Meteor impacts, while rare, remind us that Earth exists in a cosmic shooting gallery. Part 5. Galaxies and large-scale structure. Galaxy. A galaxy is a vast system of stars, gas, dust, and dark matter held together by gravity. Galaxies are the fundamental building blocks of the universe's large-scale structure. They range in size from dwarf galaxies containing just a few billion stars to giant ellipticals containing trillions of stars. The observable universe contains roughly 2 trillion galaxies, most formed in the first few billion years after the Big Bang, when dense clouds of gas collapsed under their own gravity. Over time, galaxies grow by merging with other galaxies and by pulling in new material from intergalactic space. Our home galaxy, the Milky Way, is a barred spiral galaxy about 100,000 light-years in diameter. It contains between 100 billion and 400 billion stars, including our Sun. We are located about 26,000 light-years from the galactic center in one of the spiral arms, Milky Way. The Milky Way is our home galaxy. Its name comes from the band of light visible in the night sky, which ancient peoples thought looked like spilled milk. That band is actually the combined light of billions of stars in the galactic disk, seen edge-on from our position inside it. The Milky Way is a barred spiral galaxy, meaning it has a central bar of stars with spiral arms winding outward. It contains between 100 billion and 400 billion stars, along with vast amounts of gas, dust, and dark matter. The entire galaxy rotates, with our Sun taking about 230 million years to complete one orbit. At the center of the Milky Way lurks Sagittarius A star, a supermassive black hole with a mass of about 4 million suns. The region around it is crowded with stars orbiting at tremendous speeds, some moving at several % of the speed of light. Observing these stars provided some of the strongest evidence that supermassive black holes exist. Spiral galaxy. A spiral galaxy is a galaxy with a flat, rotating disk containing spiral arms winding out from a central bulge. About 77% of observed galaxies are spiral galaxies, including our own Milky Way and our nearest large neighbor, the Andromeda Galaxy. The spiral arms are not solid structures, but density waves moving through the disk. Stars and gas clouds bunch up as they pass through these waves, triggering new star formation. This is why spiral arms appear brighter than the rest of the disk. They contain many young, hot blue stars that have recently formed. Barred spiral galaxies have a distinct bar-shaped structure in their centers, with the spiral arms beginning at the ends of the bar. Recent studies suggest that about 2/3 of spiral galaxies have bars, including the Milky Way. These bars may help funnel gas toward the central regions, fueling star formation and potentially feeding the supermassive black hole. Elliptical galaxy. An elliptical galaxy is a galaxy with a smooth, featureless appearance, ranging in shape from nearly spherical to highly elongated. Unlike spiral galaxies, ellipticals lack the flat disk and spiral arms. Their stars move on random, chaotic orbits rather than in an organized rotation. Elliptical galaxies are generally older than spirals, containing mostly old red and yellow stars. They have used up most of their gas and dust, so very little new star formation occurs. The largest galaxies in the universe are giant ellipticals, some containing trillions of stars and spanning millions of light years. Many elliptical galaxies appear to have formed through galactic collisions and mergers. When two spiral galaxies collide, their orderly rotation gets scrambled, and the result is often an elliptical galaxy. The Milky Way and Andromeda are on a collision course that will eventually merge them into a giant elliptical galaxy in about 4.5 billion years. Dark matter. Dark matter is a mysterious form of matter that does not emit, absorb, or reflect light. We cannot see it directly, but we know it exists because of its gravitational effects on visible matter. Dark matter makes up about 27% of the total mass energy content of the universe. The evidence for dark matter comes from multiple sources. Stars in galaxies orbit too fast. Without extra gravity from dark matter, they would fly apart. Galaxy clusters contain far more mass than we can see. The cosmic microwave background radiation shows patterns that require dark matter to explain. Nobody knows what dark matter actually is. It could be undiscovered subatomic particles, called weakly interacting massive particles. It could be primordial black holes formed in the early universe. It could be something entirely new that does not fit into our current understanding of physics. Detecting dark matter directly remains one of the greatest challenges in physics. Dark energy. Dark energy is an even more mysterious force that is causing the expansion of the universe to accelerate. It makes up about 68% of the total mass energy content of the universe, making it the dominant component of the cosmos. Dark energy was discovered in 1998 when astronomers studying distant supernova found that the universe's expansion is speeding up rather than slowing down. This was completely unexpected. Gravity should be pulling everything back together, but instead, space itself is expanding faster and faster. The nature of dark energy is unknown. It might be a property of empty space itself, what Einstein called the cosmological constant. It might be a new kind of energy field that changes over time, or it might indicate that our understanding of gravity needs revision. Whatever it is, dark energy will determine the ultimate fate of the universe. Galaxy cluster. A galaxy cluster is a group of galaxies bound together by gravity. Clusters can contain anywhere from a few dozen to thousands of galaxies, along with vast amounts of hot gas and dark matter. They are the largest gravitationally bound structures in the universe. The Virgo cluster is the nearest large cluster to us, located about 54 million light-years away. It contains over 1,300 known galaxies. The Milky Way is part of a smaller group called the Local Group, which itself is being pulled toward the Virgo cluster. Most of the mass in galaxy clusters is invisible. Only about 5% is in the form of galaxies. About 15% is hot gas between the galaxies, detected by X-ray telescopes. The remaining 80% is dark matter, holding the cluster together. Part 6. Cosmology and the Nature of the Universe. Big Bang. The Big Bang is the prevailing theory for the origin of the universe. According to this model, the universe began about 13.8 billion years ago from an extremely hot, dense state, and has been expanding and cooling ever since. The Big Bang was not an explosion in space. It was an expansion of space itself. Every point in the universe was once packed together in a tiny region, and that region expanded to become everything we see today. There was no center to the explosion, and no empty space for it to expand into. Space and time themselves were created in the Big Bang. Evidence for the Big Bang includes the expansion of the universe, first discovered by Edwin Hubble in 1929. It includes the cosmic microwave background radiation, the afterglow of the Big Bang detected in 1964, and it includes the abundance of light elements like hydrogen and helium, which matches predictions from Big Bang nucleosynthesis. Cosmic microwave background. The cosmic microwave background, or CMB, is the thermal radiation left over from the early universe. It is the oldest light in the cosmos, released about 380,000 years after the Big Bang, when the universe cooled, enough for atoms to form and light to travel freely through space. The CMB was accidentally discovered in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate noise from a radio antenna. They found a faint background hum coming from every direction in the sky. This discovery earned them the Nobel Prize and provided powerful evidence for the Big Bang theory. Today, the CMB has cooled to just 2.7 degrees above absolute zero. Despite being almost perfectly uniform, it contains tiny fluctuations that reveal the seeds of all cosmic structure. Dense regions in the early CMB eventually became galaxies and galaxy clusters. These fluctuations have been mapped in exquisite detail by satellites like COBE, WMAP, and Planck redshift. Redshift is the stretching of light waves as their source moves away from us, or as space itself expands. When light is stretched, it shifts toward the red end of the spectrum. This is similar to how the sound of a car horn seems lower in pitch as the car drives away. Cosmological redshift occurs because the universe is expanding. As light travels through space, the space itself stretches, making the wavelength of the light longer. The farther away a galaxy is, the more its light has been redshifted. This relationship, known as Hubble's law, allows astronomers to measure cosmic distances. The most distant objects we can see have redshifts greater than 10. Meaning their light has been stretched to more than 11 times its original wavelength. These objects are so far away that we are seeing them as they were over 13 billion years ago, when the universe was young and different from today. Hubble constant. The Hubble constant is the rate at which the universe is currently expanding. It describes how fast distant galaxies are moving away from us based on their distance. The current best estimates put it at about 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, about 3.26 million light-years, galaxies appear to be moving away about 70 kilometers per second faster. A galaxy 1 megaparsec away is receding at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. There is currently a tension in cosmology between different methods of measuring the Hubble constant. Measurements from the cosmic microwave background give slightly different values than measurements from nearby supernova. This discrepancy, if real, might point to new physics beyond our current understanding. Inflation. Inflation is a theory that the universe underwent a brief period of extremely rapid expansion in the first tiny fraction of a second after the Big Bang. During inflation, the universe expanded faster than the speed of light, doubling in size at least 80 times in less than a trillionth of a trillionth of a trillionth of a second. Inflation solves several puzzles about the universe. It explains why the universe appears so flat and uniform on large scales. It explains why the cosmic microwave background looks the same in all directions, despite coming from regions that could never have been in contact. And it explains the origin of the tiny density fluctuations that grew into galaxies. If inflation occurred, it may have created other universe bubbles beyond our observable horizon. This is the basis of the multiverse hypothesis, the idea that our universe is just one of countless universes, each with potentially different physical laws. While speculative, inflation has made predictions that have been confirmed by observations of the cosmic microwave background. Multiverse. The multiverse is a hypothetical collection of multiple universes existing alongside our own. These other universes might have different physical constants, different laws of physics, or different histories. The multiverse is not a single theory, but a collection of ideas arising from different branches of physics. Inflationary cosmology suggests that our universe might be one bubble in an infinite sea of universe bubbles, each created by quantum fluctuations during inflation. String theory suggests there might be an enormous number of possible ways to configure the extra dimensions it requires, each giving rise to a different universe with different physics. The multiverse is controversial because it may be impossible to test directly. If other universes exist, but we can never observe them, is the hypothesis scientific? Some physicists argue that the multiverse explains fine-tuning in our universe. Others argue it is untestable speculation. The debate continues. Part 7. Light, Radiation and Observation, Electromagnetic Spectrum. The electromagnetic spectrum is the full range of electromagnetic radiation, from the longest radio waves to the shortest gamma rays. Visible light, the rainbow of colors we can see, is just a tiny sliver of this vast spectrum. Most of the information in the universe is carried by light we cannot see. Radio waves have wavelengths from millimeters to kilometers. They reveal cold gas clouds, pulsars, and the cosmic microwave background. Infrared light shows us cool stars, dust clouds, and the heat signatures of distant galaxies. Ultraviolet light comes from hot stars and reveals the composition of interstellar gas. X-rays show us the hottest, most violent phenomena in the universe. The coronas of stars, gas falling into black holes, and the superheated gas in galaxy clusters. Gamma rays reveal the most extreme events: supernova explosions, gamma ray bursts, and matter annihilation near black holes. Each part of the spectrum tells us something different about the cosmos. Photon. A photon is a particle of light. Despite having no mass, photons carry energy and momentum. They are the messengers of the electromagnetic force, mediating interactions between charged particles. Every time you see something, photons are entering your eyes and triggering chemical reactions in your retinas. Light behaves as both a wave and a particle, one of the central mysteries of quantum mechanics. When light passes through a prism, it spreads out like a wave. When light hits a detector, it arrives as individual photons. This wave-particle duality applies to all quantum objects, but photons make it especially clear. Photons travel at the speed of light in a vacuum, about 186,000 miles per second. Nothing with mass can reach this speed. Photons experience no passage of time from their own perspective. A photon traveling from a distant galaxy experiences the journey as instantaneous, even if billions of years pass for us. Speed of light. The speed of light in a vacuum is exactly 299,792,458 meters per second. It is usually rounded to 300,000 kilometers per second, or 186,000 miles per second. This speed is the universal speed limit. According to Einstein's special relativity, nothing with mass can travel at or exceed the speed of light. As an object accelerates, its mass effectively increases, requiring more and more energy to accelerate further. Reaching the speed of light would require infinite energy. Only massless particles like photons can travel at this speed. The finite speed of light means we always see the universe as it was in the past. Light from the moon takes about 1.3 seconds to reach us. Light from the sun takes about 8 minutes. Light from the nearest star takes over 4 years. The most distant galaxies show us conditions billions of years ago. Telescope. A telescope is an instrument that collects and focuses light from distant objects. Telescopes allow us to see things too faint or too far away for the naked eye. They are astronomy's most important tool, revealing the true nature and extent of the universe. Optical telescopes use either lenses, mirrors, or a combination to gather and focus visible light. The first practical telescopes were built in the early 1600s. Galileo famously used one to discover the moons of Jupiter and the phases of Venus, helping overturn the Earth-centered view of the universe. Modern telescopes observe all parts of the electromagnetic spectrum. Radio telescopes use giant dish antennas to detect radio waves from space. Space telescopes, like Hubble, orbit above Earth's atmosphere, which blocks ultraviolet light, X-rays, and gamma rays. The James Webb Space Telescope, launched in 2021, observes in infrared and can see the most distant galaxies ever detected. Spectroscopy. Spectroscopy is the study of how matter interacts with electromagnetic radiation. By spreading light into its component colors and analyzing the pattern, astronomers can determine what distant objects are made of, how hot they are, how fast they are moving, and much more. Every element produces a unique pattern of spectral lines, like a fingerprint. When starlight passes through a spectrograph, we can identify which elements are present by matching the lines to known patterns. This is how we know the Sun is made mostly of hydrogen and helium, even though we have never sampled it directly. Spectroscopy also reveals motion through the Doppler effect. If an object is moving toward us, its spectral lines shift toward the blue end of the spectrum. If it is moving away, the lines shift toward the red. This technique lets us measure the rotation of stars, the orbits of exoplanets, and the expansion of the universe. Part 8. Space Exploration and Technology Rocket. A rocket is a vehicle that uses Newton's third law to propel itself through space. It works by expelling mass at high speed in one direction, which pushes the rocket in the opposite direction. Unlike airplanes, rockets do not need air to push against. They carry their own fuel and oxidizer. Chemical rockets burn fuel and oxidizer together, producing hot gas that shoots out of the nozzle at high speed. The most powerful rockets ever built include the Saturn V, which took astronauts to the moon, and the Space Launch System being developed for future lunar missions. SpaceX's Starship is designed to be the most powerful rocket in history. Reaching orbit requires tremendous speed, about 17,500 miles per hour for low Earth orbit. Most of a rocket's mass is fuel. The Saturn V weighed about 6.2 million pounds at liftoff, but delivered only about 300,000 pounds to low Earth orbit. Reusable rockets like SpaceX's Falcon 9 are revolutionizing space access by landing and flying again. Satellite. A satellite is any object that orbits another object. Moons are natural satellites. Artificial satellites are machines launched by humans to orbit Earth or other bodies. Thousands of artificial satellites currently orbit Earth, performing countless functions. The first artificial satellite was Sputnik 1, launched by the Soviet Union on October 4, 1957. It was a simple metal sphere that transmitted radio beeps for 21 days before its batteries died. Its launch marked the beginning of the space age and sparked the space race between the United States and the Soviet Union. Today, satellites provide communications, navigation, weather monitoring, Earth observation, and scientific research. The Global Positioning System uses a constellation of at least 24 satellites to provide location information anywhere on Earth. SpaceX's Starlink constellation aims to provide global internet coverage using thousands of small satellites in low Earth orbit. Space Station. A space station is a large spacecraft designed to support human habitation in orbit for extended periods. Unlike capsules or shuttles, space stations are not designed to land. They serve as laboratories, observatories, and stepping stones for deeper space exploration. The International Space Station is the largest structure humans have ever built in space. It orbits about 250 miles above Earth, traveling at about 17,500 miles per hour and completing one orbit every 90 minutes. Construction began in 1998, and it has been continuously occupied since November 2000. Astronauts on the space station conduct research in microgravity, studying everything from crystal growth to muscle atrophy. The station also demonstrates technologies for long-duration spaceflight, essential preparation for future missions to the Moon and Mars. China's Tiangong space station and private commercial stations are expanding humanity's presence in orbit. Spacewalk. A spacewalk, officially called an extravehicular activity, or EVA, is any activity performed by an astronaut outside a spacecraft. Spacewalks are essential for constructing and repairing space stations, servicing satellites, and exploring other worlds. The first spacewalk was performed by Soviet cosmonaut Alexei Leonov on March 18, 1965. He floated outside his Voskhod to capsule for about 12 minutes. The first American spacewalk followed 3 months later, when Ed White spent 23 minutes outside Gemini 4. Modern spacesuits are essentially tiny spacecraft that provide oxygen, temperature control, communications, and protection from the harsh environment of space. Astronauts face extreme temperatures ranging from over 250 degrees Fahrenheit in sunlight to minus 250 degrees in shadow. Spacewalks remain dangerous, requiring extensive training and careful planning. Space probe. A space probe is an unmanned spacecraft designed to explore beyond Earth orbit. Probes have visited every planet in our solar system, landed on moons and asteroids, and traveled to the very edge of interstellar space. They are our robotic ambassadors to the cosmos. The Voyager probes, launched in 1977, are the most distant human-made objects. Voyager 1 is now over 15 billion miles from Earth, officially in interstellar space. Both probes carry golden records containing sounds and images representing life on Earth. A message in a bottle for any extraterrestrial civilization that might find them. Current probes are exploring Mars, Saturn, asteroids, and more. The Mars Perseverance rover is searching for signs of ancient life. The New Horizons probe, after flying past Pluto in 2015, continues into the Kuiper Belt. Future missions will explore the moons Europa and Titan, searching for conditions that might support life. Part 9: Exoplanets and the Search for Life. Exoplanet. An exoplanet is a planet that orbits a star other than our Sun. The first confirmed exoplanet around a Sun-like star was discovered in 1995. Since then, astronomers have confirmed over 5,600 exoplanets, with thousands more candidates awaiting confirmation. Exoplanets come in astonishing variety. Hot Jupiters are gas giants orbiting so close to their stars that their years last only days. Super-Earths are rocky planets larger than Earth but smaller than Neptune. Some planets orbit to stars, like the fictional Tatooine. Others have been ejected from their systems and drift alone through interstellar space. Finding exoplanets is challenging because stars are so bright and planets so small and dim. Most exoplanets are detected indirectly, either by watching for the tiny dimming as a planet passes in front of its star, or by measuring the wobble the planet's gravity induces in its star. Only a handful have been directly imaged. Habitable zone. The habitable zone is the region around a star where conditions might allow liquid water to exist on a planet's surface. It is sometimes called the Goldilocks zone because the temperature is not too hot and not too cold, but just right for life as we know it. The habitable zone depends on the star's temperature and brightness. For our Sun, the habitable zone extends roughly from 0.95 to 1.4 astronomical units. Venus, at 0.72 AU, is too hot. Mars, at 1.520, is on the outer edge and too cold today, though it may have been habitable in the past. Being in the habitable zone does not guarantee habitability. A planet also needs the right atmosphere, magnetic field, and geological activity. Mars is in the habitable zone, but lost most of its atmosphere and surface water. Venus, closer to the Sun, suffered a runaway greenhouse effect. Earth's particular conditions make it special. Biosignature. A biosignature is any substance or phenomenon that provides scientific evidence of past or present life. On distant exoplanets, astronomers search for biosignatures in atmospheric spectra, looking for gases that should not exist together without biological processes to maintain them. On Earth, the combination of oxygen and methane in the atmosphere is a strong biosignature. Without life constantly replenishing them, these gases would react with each other and disappear within a few million years. Finding a similar combination on an exoplanet would be exciting, though not proof of life. Future missions will be designed specifically to detect signs of life on nearby Earth-like planets. If we find biosignatures, it will be one of the most profound discoveries in human history. Fermi paradox. The Fermi paradox is the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them. The physicist Enrico Fermi supposedly asked, "Where is everybody?" Given the age and size of the universe, intelligent life should be common. Yet we see no signs of it. Many solutions have been proposed. Perhaps life is rarer than we think. Perhaps intelligent civilizations destroy themselves before they can spread. Perhaps they exist but are too far away. Perhaps they are here but we do not recognize them. Perhaps we are among the first intelligent species to evolve in the universe. The Fermi paradox has profound implications. If we are alone, the universe is ours to explore, but lonely. If civilizations typically destroy themselves, we face a warning. If they are out there and we have not found them, perhaps they are hiding, or perhaps the universe is stranger than we imagine. SETI stands for Search for Extraterrestrial Intelligence. It is the collective name for scientific efforts to detect signs of intelligent life beyond Earth, primarily by searching for artificial signals like radio transmissions or laser pulses. Modern SETI began in 1960 when astronomer Frank Drake pointed a radio telescope at two nearby stars and listened for signals. Since then, SETI has expanded to scan millions of stars using increasingly powerful telescopes and sophisticated analysis techniques. No confirmed extraterrestrial signals have been detected. SETI faces enormous challenges. The universe is vast, and we do not know what frequencies or signal types to look for. An alien civilization might use communication methods we cannot even imagine. Despite decades of searching, we have only examined a tiny fraction of the possible search space. The search continues. Part 10. Cosmic Phenomena Eclipse An eclipse occurs when one celestial body passes into the shadow of another. Solar eclipses happen when the moon passes between Earth and the sun, blocking sunlight. Lunar eclipses happen when Earth passes between the sun and moon, casting its shadow on the moon. Solar eclipses are spectacular because the moon happens to appear almost exactly the same size as the sun in our sky, despite being 400 times smaller but also 400 times closer. During a total solar eclipse, the moon completely covers the sun, revealing the corona, the sun's outer atmosphere, in a breathtaking display. Lunar eclipses are visible from anywhere on the night side of Earth, making them more commonly observed. During a total lunar eclipse, the moon turns a deep red color because Earth's atmosphere bends some sunlight around the planet and onto the moon. The red color comes from the same phenomenon that creates red sunsets. Aura. An aura is a natural light display in the sky, primarily seen in high-latitude regions. The aurora borealis, or northern lights, occurs in the northern hemisphere. The aurora australis, or southern lights, occurs in the southern hemisphere. They are among the most beautiful phenomena visible from Earth. Auroras are caused by charged particles from the sun interacting with Earth's magnetic field and atmosphere. The particles are channeled by the magnetic field toward the polar regions, where they collide with atoms of oxygen and nitrogen in the upper atmosphere. These collisions excite the atoms, which release energy as light. The colors of auroras depend on which atoms are involved and at what altitude. Oxygen at high altitudes produces rare red auroras. Oxygen at lower altitudes produces the most common green. Nitrogen produces blue and purple. Auroras can stretch hundreds of miles across the sky and dance for hours. Solar flare. A solar flare is a sudden, intense burst of radiation from the sun's surface. Flares release enormous amounts of energy across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. A single large flare can release energy equivalent to billions of nuclear bombs. Flares occur when magnetic field lines in the sun's atmosphere become twisted and stressed, then suddenly snap and reconnect. This releases stored magnetic energy in a flash. The most powerful flares are classified as X-class and can affect radio communications, satellite operations, and power grids on Earth. The radiation from a solar flare reaches Earth in about 8 minutes, traveling at the speed of light. Often flares are accompanied by coronal mass ejections, huge clouds of plasma that take 1 to 3 days to reach Earth. These can cause geomagnetic storms, triggering auroras and potentially damaging infrastructure. Gamma ray burst. A gamma ray burst is the most energetic type of explosion known in the universe. For a few seconds or minutes, a gamma ray burst can outshine entire galaxies. They were first detected in the 1960s by military satellites designed to detect nuclear tests. Long gamma ray bursts, lasting more than 2 seconds, appear to result from the collapse of massive stars into black holes. Short gamma ray bursts, lasting less than 2 seconds, seem to come from mergers of neutron stars or neutron stars and black holes. Both types involve jets of material shooting out at nearly the speed of light. A gamma ray burst pointed directly at Earth from within our galaxy could be catastrophic, potentially stripping away the ozone layer. Fortunately, such events are extremely rare, and the nearest known gamma ray burst sources are thousands of light years away. We are relatively safe for the foreseeable future. Gravitational waves. Gravitational waves are ripples in the fabric of space-time caused by accelerating massive objects. They were predicted by Einstein in 1916 as a consequence of general relativity, but were not directly detected until 2015, a century later. The first detection came from the LIGO Observatory, which measured the gravitational waves from 2 black holes merging about 1.3 billion light-years away. The black holes, with masses of about 36 and 29 times the Sun, spiraled together and merged, releasing energy equivalent to 3 solar masses in pure gravitational wave energy. Gravitational wave astronomy has opened a new window on the universe. We can now detect events invisible to light, like black hole mergers deep inside gas clouds. Combined with traditional observations, gravitational waves provide multi-messenger astronomy, telling us more about cosmic events than either method alone. Part 11. The Future of the Universe. Heat death. The heat death of the universe is a possible ultimate fate in which the cosmos reaches a state of maximum entropy or disorder. All usable energy would be exhausted, all stars would have burned out, and the universe would become a cold, dark, uniform void with nothing happening. This scenario assumes the universe continues expanding forever, which current observations support. But over trillions of years, stars will exhaust their fuel and die. Galaxies will evaporate as stars are flung out by gravitational interactions. Black holes will dominate, then slowly evaporate through Hawking radiation over time scales longer than comprehension. Eventually, even protons might decay, though this has never been observed. After unimaginable spans of time, perhaps 10 to the power of 100 years or more, the universe would contain nothing but scattered particles at temperatures barely above absolute zero. No stars, no life, no change. Just endless, silent darkness. Big Crunch. The Big Crunch is an alternative fate for the universe, in which the expansion eventually reverses and everything collapses back into a singularity. This would be the opposite of the Big Bang. A Big Crunch, bringing all matter and energy back together in a final cosmic implosion. For the Big Crunch to occur, the universe would need enough matter to halt and reverse the expansion. Current observations suggest this is not the case. The universe's expansion is actually accelerating, driven by dark energy. Unless dark energy changes its behavior, a Big Crunch seems unlikely. Some theories suggest the universe might be cyclic, with big bangs and big crunches repeating forever. Each cycle would begin with an explosion, expand, contract, crunch, and explode again. This elegant picture remains speculative, but it offers a vision of eternal cosmic rebirth. Big Rip. The Big Rip is a hypothetical scenario in which dark energy grows stronger over time, eventually tearing apart everything in the universe. First, galaxy clusters would be pulled apart, then galaxies themselves, then solar systems, then planets, then atoms, then even the fabric of space-time itself. This scenario requires a particular type of dark energy called phantom energy that becomes more powerful as the universe expands. Current observations do not clearly support or rule out phantom energy. If it exists and grows as predicted, the Big Rip could occur in roughly 20 billion years. In the final moments before a Big Rip, expansion would become so violent that individual particles would be torn apart. The universe would essentially disintegrate into nothing. This is perhaps the most dramatic possible ending for the cosmos, a final explosive unraveling of everything that exists. Conclusion. We are made of star stuff, and so we come to the end of our journey through the language of space. We have traveled from the basics of light and gravity to the strange depths of black holes. We have explored our cosmic neighborhood in the solar system and ventured out to distant galaxies and the edges of the observable universe. We have looked back to the Big Bang and forward to possible endings trillions of years from now. Along the way, we have learned that the universe is stranger and more wonderful than any fiction. Stars explode and seed the cosmos with the elements that make planets and people. Gravity bends space and time. Light shows us the past. Dark matter and dark energy control cosmic destiny, even though we cannot see them. And somewhere out there, perhaps other beings look up at their own alien skies and wonder if they are alone. The astronomer Carl Sagan famously said that we are made of star stuff. The carbon in our bodies was forged in the hearts of ancient stars. The oxygen we breathe was scattered by supernova billions of years ago. The iron in our blood came from the death throes of massive stars. We are not separate from the universe. We are part of it. We are the universe becoming aware of itself. Understanding space is not just about memorizing definitions and facts. It is about recognizing our place in the cosmic story. We live on a small, rocky world orbiting an ordinary star in the suburbs of an average galaxy among trillions of galaxies. And yet from this tiny platform, we have reached out and touched the cosmos. We have sent our machines to other planets. We have decoded the light from stars billions of light years away. We have begun to understand the laws that govern everything from the smallest particle to the largest supercluster. This is the gift of astronomy. It humbles us by revealing how small we are, and it elevates us by showing what we can understand. Every term in this dictionary represents a hard-won piece of knowledge, earned by generations of curious minds, looking up and asking questions. So, the next time you look up at the night sky, remember what you have learned. Those tiny points of light are not just decorations. They are suns, some larger and hotter than our own, some smaller and cooler. Around many of them orbit planets where it might rain diamonds or snow iron. Between them stretches the near-perfect vacuum of interstellar space, dotted with clouds of gas that will one day collapse into new stars. And all of it is rushing away from us as the universe continues its ancient expansion. The cosmos is calling. It always has been. And now you have the words to answer. Good night and clear skies.